So in this video, we're going to do more U-substitutions. So I've got a function, and I'm going to integrate, find the antiderivative, the indefinite integral of x cubed times x to the fourth minus 1 raised to the fifth power dx. So when I use U-substitution, I need to find an inside function. I see something raised to a power. I automatically start thinking, hey, look, this inside function here is x to the fourth minus 1. Another bingo for me is that when I take the derivative of x to the fourth, I get an x cubed factor. And so I see an x cubed factor sitting out right here. So that makes me even more confident that u equals x to the fourth minus 1 is my u substitution. So to find the differential, I take the derivative of u, I get du. The derivative, the differential here of x to the fourth is 4x cubed, and then the derivative here is 0. So 4x cubed dx is my differential for du. Okay? Now I'm going to make number 2 after I computed my differential. Number 3 says to transform the integral into u's only. Okay, so we're going off of our steps here. And so I'm transforming my integral into u's only at this point after I compute the differential. So when I do that, I get integral, and I replace everywhere I see an x to the fourth minus 1, I put a u there, so it's u to the fifth. And then if I do that with that piece here, what do I have left? Well, I've got an x cubed and a dx. So I write the x cubed and the dx. I need to get rid of this with my differential, but I have a problem. So I have an x cubed dx here, but I have a 4x cubed dx here. So there's two ways to handle this. Option number 1 is I make this 4x cubed look like x cubed dx here, okay? So how do I do that? Well, I solve for x cubed dx here. To do that, I divide both sides by 4. And so what do I get? I get x cubed dx is equal to 1/4 du. And so once I've done that, now I can substitute. I'm going to replace the x cubed dx with 1/4 du. And now I can simplify here. And whenever I simplify here, I'm going to have the 1/4 coefficient rule, bring it the 1/4 out front. And then whenever I integrate u to the fifth, I get u raised to the sixth divided by 6 plus c. To simplify this, 1/4 times 1/6 gets me 1/24. And then I want to replace the u to get back in terms of x, right? Solve the integral and write in terms of x. So I solved the integral here. Now I'm writing my final answer in terms of x. So what do I replace u with? U is x to the fourth minus 1. So I plug that in here, and it's raised to the 6th power. Uh-oh, that needs to be raised to the 6th power right there. Okay? So option 2, what does option 2 say to do? So option 1, we made the differential look like what was inside the integrand here, okay? Option 2 says just solve for dx, and then you'll figure it out. So what do I mean by that? So we took the derivative, we got the differential here. To solve for dx, what I would do is I would get dx by itself by dividing both sides by 4x cubed. And so once I divide both sides by 4x cubed, my dx is equal to du divided by 4x cubed. So everywhere I see a dx, I'm going to replace it with du divided by 4x cubed. And so I have u to the fifth, x cubed, multiplied by dx. Well, what does dx equal? Dx is equal to du divided by 4x cubed. And what do I notice at this point? The x cubed and the x cubed cancel each other. And so what do I get? I get this right here, u to the fifth, and then I have 1/4 du. And guess what? This is exactly the same as what I had right here. And so I work through the math and I get to the exact same answer right there, okay? So either way you want to go with this, doesn't matter. You're going to get the same answer every time. So when you see that your differential doesn't match up, you can either solve the differential for dx and then replace the dx in here and then simplify everything else, or you can algebraically manipulate the differential to look exactly like what's here in the integrand there. And to do that, I would divide by 4 right there to make it look like what we have over there. So 2 options, really it's whatever floats your goat on this one. Not too picky on which one you try to go with, because both of them will work for you every time. Let's do another problem. U-substitution again. So first thing I got to do is I got to figure out what's going to be my inside function. Well, anytime I have a square root, I automatically think whatever's in the square root is going to be my inside function. Is that always the case? No, it's not. It's trial and error with U-substitution. If you do a U-sub and you can't get everything in terms of U, you got U's and X's, then you made the bad U-sub if you did it right. So let's pick u equal to the inside here, x squared plus 1. Then I can replace this nasty thing with the square root of u, which we know to be u to the 1/2 here. Okay, so that's where that's coming from there. Right, now to take the differential, the derivative of u is 2x dx. That's a differential there. But I've got a situation again. The only thing, look, I took care of the denominator with this here. So all I have left is this x dx here, but I have 2x dx there. So it's, once again, it's your preference if you want to solve for x dx or if you want to solve for dx. I don't care which one you do. You just be consistent with what you choose. So what I'm going to do is I'm just going to solve for x dx because I like to replace what I see in here in the integrand. And when I do that, I divide both sides by 2. So if I divide both sides by 2, then I have 1/2 du equals x dx, which is exactly what I see there. So I'm going to replace that numerator with 1/2 du. Okay, so now I want to simplify this. So to simplify, I'm going to pull the 1/2 out front. So the constant, pull it out front. And then the u to the 1/2 in the denominator. If I have 1 over u to the 1/2, then if I flip u to the numerator, it becomes negative 1/2 there. Okay? So when I use my power rule here for integration, first off, I've got my constant. I pull the 1/2 out front, right? But to integrate u to the negative 1/2, I add a half to negative u. I add 1 to negative a half, and I get 1/2, and then I divide by that 1/2. But guess what? 1/2 and 1/2 cancel to just get 1. And so I have u to the 1/2 plus c. So that's a square root of u, but what is u equal to? U is equal to x squared plus 1. So square root x squared plus 1 plus c. This next one here, I'm going to need to use some properties of logarithms. If you think back to a property of logarithm, if I have ln of x to the r, this is like r times the ln of x. Okay, why does that work? Well, let's think about this. ln of x squared. Remember, x squared is like ln of x multiplied by x. And if I have multiplication in the argument of logs, that's the same as adding those logs. And so I have 2 ln x, 2 of those ln x's there. So you see how we skip from having the 2 in the exponent here to having it as a coefficient out front, just like that. So that's what that rule does there. So I'm going to use that rule to my advantage here. To simplify first. If you can simplify, simplify. Promise you to make your life a little bit easier. So I simplify, bring the x out to the front, okay? And so I have integral of 1 over x ln x dx. Now I'm going to make a u substitution. So I'm going to choose u to be the more complicated one, ln x. And then the derivative of ln x is 1 over x dx. That's the differential there. So I'm going to rewrite this. I'm going to write it as three different things. 1 over x, 1 over ln x, and dx. The reason I write it out separately like this is so it's easy to do a substitution here. So I see that my 1 over x dx is right here, so I can replace what's highlighted with the simple du. That makes that pretty easy. And I can replace the ln x with the u there. So my integral is 1 over u, okay? And then the du comes from right here. Hope the colors kind of help you put everything together. All right, so now I need to integrate 1 over u du. Well, guess what? The integral of 1 over u is ln absolute value of u, pretty cool, plus c. But what does u equal? U, I need to replace it, put it back in terms of x. Since I started in terms of x, I need to finish in terms of x. So I replace u with ln x. So it's the absolute value ln of x. So it's the ln of absolute value ln of x plus c. Interesting, right? So that, my friends, are 3 examples for u substitution right there for you.